Hello dear students, welcome to the channel and welcome to this playlist in which we are discussing the second module of instrumentation and sensors. In this module up until now we have seen different types of sensors and we have classified these sensors based on whether they are analog or digital and whether their applications, what they serve, plus the ranges that they serve in. Except that we have seen if my installation of sensor requires permanent installation or temporary installation. We have seen how do we select a particular sensor and how do we find the sighting of that particular sensor. Then we have also discussed about a case study of North Carolina University in which we have seen selection, setting and installation of some of these sensors which we have discussed about. And then we have also seen operating modes of some of these sensors as well. And today we are going to discuss about errors in measurement or uncertainties in measurement in particular, but will require the knowledge of previous classes. So if you haven't checked out previous videos, link will be flashing on the top right hand side corner of your screen in the I button, so you can click on it and you can check it out. And if you have already seen it, so let's start with today's class. So first, the term error. What do you call an error? Not in general terms or not in physical or philosophical terms, but in measurement, what do you call error? So error in the measurement system can be actually divided into those that arise during the measurement process and those that arise due to later corruption of the measurement signal by some noise during the transfer of the signal uh, from the point of measurement to some other point or any other way, right? So as you know, it is very important in any measurement system to reduce the error to the minimum possible level and then to quantify the maximum remaining error that may exist in any other instrument output reading, right? So what basically is error? So error is the difference between the two values. Now what values? So the actual value of the measurement or the true value of the measurement and the measured value, right? So the subtraction or difference between these two gives you the value of error. Now in some cases it is not as simple as that, right? There is a further complication that the final output from a measurement system is calculated by combining together two or more than two instruments or measurement of separate physical variables. So in such cases what do? We have to take special consideration, right, in order to determine the calculated error level in such separate measurement, and then we have to combine them together to give best estimate of the most likely error magnitude in the calculated output quantity, and that is what exactly we are going to discuss here. So once you identify error, what do? You try to either eliminate it or you try to reduce it as much as you can. So the starting point in this quest is to reduce reduce the induction of error or incidence of error arising due to the measurement process, is to carry out a detailed analytics of all error sources in the system, right? So each of these error sources can be considered in turn, looking for different ways of elimination or at least reducing the magnitude of that error. So these errors which are arising because of the measurement process can be divided into two groups: systematic and random errors. And now we are going to see both of them in detail. So let's first discuss about the systematic error. So the systematic error describes errors in the output reading of the measurement system that are consistently on one side of the correct reading, right? Like either all the errors are positive side or all the errors are on the negative side. So two major sources of systematic errors are system disturbance during measurement and effective environmental changes, right? uh, or you can also put it in a way of modification of inputs, right? Because due to modification of inputs there will be uh, this effect will be visible, right? Because of environmental changes you will see the modification in inputs or changes in inputs. Now other sources of systematic errors will include uh, bent meter needles, the use of uncalibrated instruments, and that is why we always say that do not use uncalibrated instruments. The drift in the instrument characteristics and poor cabling practices. And even when systematic errors due to the above factors have been reduced or eliminated, some errors remain that are inherent in the manufacturer or into the instrument itself. So these are the quantified, these errors are quantified by the accuracy figure which are quoted in the published specifications which contained in the instrument data sheet itself, and you can find it on web, or you can get it the physical copy of the data sheet of that particular instrument whenever you purchase it. So that is your systematic error, right? It will either be positive, all the errors will be on the positive side, or all the other errors will be on negative side. Then we have the random error. So random errors are perturbations of the measurement either side of the true value caused by random or unpredictable effects, such that the positive errors and negative errors occur in approximately equal number for series of measurement that made of sample quantity. And such perturbations are mainly small, but large amount of this perturbations occur from time to time. And again, this will be very unpredictable. So the random errors often arise when the measurements are taken by human observations of an analog meter. And that is the reason that we don't often see the random errors very frequently nowadays, because we are using digital meters a lot. But back in the time when analog meters were being used very frequently, the random errors used to play their part, right? So especially when interpolation is involved between two scale points, we see random errors. Then the electrical noise that can also be a source of random error, and to a large extent random error can be overcome by taking the same measurement a number of times and extracting the value by averaging or other statistical techniques, which we are going to see in the next class. But any quantification for the measurement value and statement of the error bound remains a statistical quantity, and because of the nature of this random errors, the fact that the large contributions in the measurement quantity occur from time to time, and the best that we can do is to express measurement in probabilistic terms, right? So we may be able to assign 95% or even 99% confidence level that the measurement is certain value within error bound of, let's say, plus or minus 1% or plus or minus 4% or plus or minus 5%. But there is a fact that we can never attach 100% probability to measurement value that are subjected to the random errors. Now what would be the difference between systematic and random errors? So the error sources in the measurement system must be examined carefully to determine whether the type of error which is present is systematic error or a random error, and then you have to apply the appropriate treatment based on the type of error. So in the case of manual data measurement, human observer may make different observation at each attempt, but it is often reasonable to assume that the errors are random, and then the mean of these readings is likely to be close to the correct value. However, this is only true as long as the human observer is not introducing the parallax, right? Which is induced systematic error, and it will also persistently reading the position of the needle against the scale of what? Scale of analog meter, from one side rather than from directly above, right? So do you understanding that you're not watching straight, right? You're watching in cross. So because of this, there would be some error because of the uh, watching something in a crossed way. So that is one case, and in that case, how do you do the correction, right? Because this is a systematic error. So in that case, the correction would have to be made for this systematic error in the measurement before statistical techniques were applied to reduce the error of random errors. Then you would have to identify the source of the systematic error. In previous case you have identified, but let's see some other cases. So system errors in the output of many instruments are due to factors inherent in the manufacturer of the instrument, arising out of the tolerance in the components of the instrument itself. So they can also arise due to wear in the instrument components over a period of time. And in some cases, what happens, the systematic errors are introduced either by the effect of environmental disturbances or through the disturbance of the measured system by an act of the measurement, right? So these various sources of systematic errors and ways in which the magnitude of the errors can be reduced. And let's see these ways how we can reduce the systematic errors. So first is the system disturbance due to measurement. So the disturbance of the measured system by the act of measurement is a common source of the systematic error. And if you were to start with the beaker of hot water and wish to measure the temperature of it with a mercury in a glass thermometer, then what would you do? You take the thermometer uh, in which would the initially be at a room temperature, and then plunge into that water. And while doing that, we would be introducing a relatively cold mass, which is thermometer, into the hot water, and a heat transfer would take place between the water and the thermometer. So this heat transfer would lower the temperature of water, correct or not? Because what does the zeroth law of thermodynamics says, if you remember, right? So there will be heat transfer from lower from hot water to cold water, right? So whilst the reduction of this temperature in this case would be so small that it would be undetectable by the limited measurement resolution of the thermometer, but the effect is finite, and it is clearly established in the principle that it is nearly all measurement situations the process of measurement disturbs the system and alters the value of the physical quantities which is being measured. So a particular important example of this will occur with the orifice plate. If you have seen the orifice plate, this is the placed into the fluid carrying pipe to measure the flow rate of the flowing liquid. So this is a function of the pressure that is measured either side of the orifice plate, and this measurement which is produced causes a permanent pressure loss in the flowing fluid. So the disturbance of the measured system can often be very significant, And thus, as a general rule, the process of measurement always disturbs the system which is being measured. And the magnitude of the disturbance will vary from measurement system to the next and will be affected particularly by the type of instrument which is used for for that measurement purpose. So different ways of minimizing disturbance from measured system is very important consideration in instrument design, but accurate understanding of mechanism of system disturbance is prerequisite for this. Then we have the instrument in electrical circuit. So in analysis system, disturbance during the measurement in electrical circuits, like we have the Thevenin theorem and Norton theorem. So for this case, let's take Thevenin theorem, which is often a great assistance for understanding the measurement errors in electrical circuit. For an instance, consider a circuit which is shown here. This circuit, see, it has resistance R1, R2 and R3, R4 and R5, and it has two batteries E1 and E2 connected to it, and they are going to load, and the load is connected with a voltmeter. Now, for the purpose of defining equivalent single resistance of the circuit by Thevenin theorem, all voltage sources are presented by the internal resistance, which can be approximated to zero, as you all know. See, in this case, we have considered the internal resistances, right? Internal resistance is almost zero, always close to zero. Now see, voltage across the resistor R5 is to be measured by a voltmeter with resistance Rm, and here Rm will act as a shunt resistance across R5, as you can see, right? Rm will act as a shunt resistance across R5. So it will decrease the resistance between AB point, and hence it will disturb the circuit, and therefore the voltage which is EM, which is measured by the meter, will not be the exact value of the voltage E0, which exists prior to the measurement, right? So the extent of the disturbance can be accessed by the calculating open circuit voltage E0 and comparing it with the EM. And what does Thevenin's theorem does? It allows the circuit, which you can see in the image, that comprises two voltage sources and five resistors to be replaced by an equivalent circuit which will contain only a single resistance and single voltage source only, right? Something like this. It consists of single voltage source and single resistance only. So for that purpose of defining the equivalent single resistance of the circuit by Thevenin's theorem, all voltage sources are represented by their internal resistance, and which can be approximated to zero, as I've said earlier, right? So analysis which is proceeds by calculating the equivalent resistance of selection of the circuit and building this up until the required equivalent resistance of the whole of the circuit is obtained, and then starting at C and D, the circuit to the left C and D will consist of series pair of the resistance R1 and R2, as you can see, and will be in parallel with R3. So the equivalent resistance can be written as this, right? R1 plus R2 plus 1 by R3. And then when you move to A to B, the circuit to the left will consist of pair of series resistances in parallel with R5, and equivalent circuit resistance RAB can thus be written as this circuit. And when you finally take the sum, the final value of RAB would look something like this. Now defining I as the current flowing through the circuit when the measuring instrument is connected to it, the value would be RAB plus RM would be in denominator and E0 would be in numerator. And the voltage which is measured by the meter would be RM E0 divided by RAB plus RM, right? So what did we do? We simply took V equal to IR because RM is the resistance and this is the value of I, as you can see here. Now in the absence of the measuring instrument and in the resistance RM, this voltage across the AB would be equivalent circuit voltage across the voltage source whose value is E0, and the effect of the measurement is therefore to be reduce the voltage across AB by the ratio which is given by EM divided by E0 would be equal to RM divided by RAB plus RM. So thus it obtains that RM gets larger and the ratio EM divided by E0 will get close to unity. And slowing the design strategy, it should be to make RM as high as possible to minimize the disturbance of the measured system. Then they have given the example. You can try that example as well. But moving ahead, let's see the errors which are caused because of the environmental outputs. The second topic which we were to see. So this environmental inputs is defined as the apparently real input to the measurement system, which is caused by the change in the environmental conditions surrounding that measurement system itself. Now these specified conditions must be reproduced as closely as possible during this calibration exercise, because away from the specified calibration conditions the characteristics of measuring instruments will vary to some extent and it will cause the measurement error. Now this magnitude of this environmental which is induced variation of quantified by two constants which are known as the sensitivity drift and zero drift. So these variations of environmental conditions which are away from the calibration conditions are sometimes described as modifying inputs to the measurement system because of the modifying the output of the system. And when such modifying inputs are present, then it is often difficult to determine how much of the output change in the measurement system is due to change in the measurement variable and how much is due to the change of environmental conditions. Let's take an example to understand that. Suppose that we are having a small closed box and have been told that it may contain either mouse or a cat, and we are also told that the box weighs 0.1 kilogram or 100 grams when it is empty. So if we put a box onto the bathroom scale and observe the reading of 1 kg, that does not immediately tell us what is in the box because of the reading may be due to one of the three things. Which three things? First one, a zero point 0.9 kg rat is in the box, which can be real input, or an empty box with a zero point 0.9 kg bias on the scale due to the temperature change, which is the environmental input, and a zero point 0.4 kg mouse in the box together with a zero point 0.5 kg bias, which means there is a real input plus there is an environmental input, right? So thus the magnitude of any environment input must be measured before the value of the measured quantity, right? So the magnitude of any environmental input must be measured before the value of the measured quantity and can be determined from the output reading of an instrument as well. And in very general measurement situation, it is very difficult to avoid environmental inputs because it is either impractical or impossible to control the environmental conditions or surrounding of the measurement system. So system designers are therefore charged with the task of either reducing the susceptibility of the measuring instrument to environmental inputs, or alternatively quantifying the effects of the environmental inputs and correcting them for the instrument output reading. Now let's see wear and tear, wear in the instrument components, right? So there are some techniques to deal with environmental inputs and minimize their effects, and that is what we are going to see now. So first one is the wear in the instrument component. So systematic errors can be frequently developed over a period of time, and because of wear in the instrument component that happens. So recalibration required to be done in order to solve this problem. After that, we have the problem of connecting leads, and it is very common problem. So in the connection of a component of the measurement system, a common source of error is the failure to take proper account of the resistance of connecting leads, right? And for an instance, in typical applications of resistance thermometer, it is common to find that the thermometer is separated from the other parts of the measurement system by perhaps 100 meters. So the resistance of such length of 20 gauge copper wire would be 7 ohm. And there is further complications that such wire has a temperature coefficient of 1 milliohm per degree Celsius. So the careful consideration required to give to the choice of the connection leads, and not only should they be adequate cross section so that the resistance is minimized, but they should also adequate screened if they are thought likely to be subject to electrical or magnetic fields that could otherwise cause induced noise, right? So where screening is thought essential, then the routing of the cables also required careful planning, right? So there is one of the famous examples which has been mentioned here in one application in author's personal experience of author of this book, particularly Alan Morris. If you want to know about him, his name is Alan Morris. So uh, one of his personal experience, which involved instrumentation of electrical arc steel making furnace, screened signal carrying cables between transducer on the arc furnace and a control room at the side of the furnace were initially corrupted by the high amplitude 50 Hz noise. But by changing the route of the cables between the transducer and the control room, the magnitude of this induced noise was reduced by a factor of about 10. So just think about it. How much difference does it causes? Then let's see the reduction of systematic errors. And if you remember, we discussed about this earlier as well, that the prerequisite for the reduction of the systematic error is the complete analysis of the measurement system that identifies all sources of errors, right? Simple faults within the system like bent meter, needles, and poor cabling practices can usually be readily and cheaply rectified by once they have been identified. So you first require to identify it, but there are some other error sources which are required more detailed analysis and treatment, and different approaches to error reductions are considered, which are given which are being discussed now. So first one among them is careful instrument designing. So it is very useful in environmental inputs. So by reducing the sensitivity of an instrument to environmental input as low level as possible, we can uh, win the battle against the environmental inputs. For instance, in the design of a strain gauge, the elements should be constructed from a material whose resistance has very low temperature coefficient, right? Which means the variation of the resistance with temperature would be very small. But the error because of the way in which the instrument is designed are not always easy to correct, and the choice often has to be made between the high cost of redesigning the whole equipment and the alternative of the accepting the reduced measurement accuracy if redesign is not undertaken, right? So it is very important, the designing of an instrument. Second point would be the method of opposing inputs that compensates for the effect of the environmental inputs in the measurement system by introducing equal and opposite environmental inputs that cancels it out, right? Simple example of this technique is applied in the type of millivolt meters, as you can see in figure 3.2, let me show you. See, in millivolt meters they have simply cancelled each other out. Now let's come here, right? Let's read first what they've done. So it consists of coils suspended in a fixed magnetic field produced by a permanent magnet. So when unknown voltage is applied to the coil, the magnetic field, because of the current, interacts with the fixed field and causes the coil to turn. And if the coil resistance is sensitive to the temperature, then any environmental input to the system in form of a temperature change will alter the value of the coil current for a given applied voltage, and so alter the point of output reading as well, right? Which will compensate, in compensation for this is made by the introducing compensating resistors R comp in this circuit, and where R comp is the temperature coefficient that is equal to the magnitude, equal to the equal in magnitude but opposite in sign, so that uh, the coil can be nullified, resistance of the coil can be nullified, right? So thus in response to increase in temperature, R coil increases but R composition decreases, and so the total resistance will remain approximately the same, right? So you can see here, this is the coil and this is the R comp, which is compensating resistance. Then we have the high gain feedback. The very benefit for adding high gain feedback to many measurement system is stated by considering the case of the voltage measuring instrument. Uh, Let me show you this one, simple block diagram of a voltage measuring instrument. Now let's see what they have done. In this system, the unknown voltage IE is applied to the motor of torque constant Km, and the induced torque will turn the pointer against the restraining action of the spring with spring constant Ks. So the effect of the environmental input on the motor and the spring constant is represented by the variables dm and ds. Now in the absence of the environmental inputs, the displacement of the pointer x0 will be given by x0 equal to km ks ei, right? So in the presence of the environmental inputs, both km and ks will change, and the relationship between x0 and ei can be affected greatly as well. So what would you do? It would become very difficult or even impossible to calculate the value of ei from the measured value of x0. So now consider what will happen if the system is converted into the high gain or closed loop one, right? This is still open loop. What will happen when you convert it to the high gain closed loop system? So by adding amplifier of a gain constant K and feedback device with the gain constant Kf, assume also the effect of the environmental input on the values of the K and Kf are represented by dA and dF. So the feedback devices feeds back a voltage E0 proportional to the point displacement x0, and this would be compared with the unknown voltage ei by comparator, and then the error will be amplified. See, right? Here you have dA, dc, ds and df. So what are you doing? Error is getting amplified, as you can see here. Now what would you do? It would tell you ei, k, km and ks will be equal to 1 plus kf, km, ks into x0, and based on that you would find the value of x0. Now because k is very large, because it is a high gain amplifier, the value of k, kf, km and ks, multiplication of all four of them, would be greater than 1. So this equation will be reduced to x0 ei, this part, divided by kf, because these three would be too high that they would cancel out each other. See, because it would be too greater than 1, so the 1 will not hold any significance here. So This is highly important result because we have reduced the relationship between x0 and ei to one that involves only kf. So the sensitivity of the gain constant ka, km and ks to the environmental inputs da, dm and ds has therefore been rendered irrelevantly, and we are only have to concern with one environmental input only, which is df, right? Convenient or not? And making it more convenient, it is usually easy to design a feedback device that is insensitive to environmental input, right? So it is much easier than trying to make the motor or spring insensitive, and because of that, the high gain feedback techniques are more often a very effective way of reducing measurement system sensitivity to environmental inputs. But one potential problem that must be mentioned is that there is a possibility that high gain feedback will cause instability in the system, and because of that, any application of this method must include careful stability analysis of the system. Now let's see other few points. First one is the calibration, because calibration, as I've said, is very important. Considering in measurement system and calibration process are considered in detail as well in upcoming chapters when we discussed it, but all instrument suffer drift in these characteristics, and the rate in which it happens depends on many factors like environmental conditions in which instruments are used and used very frequently in their use. So errors due to instruments being out of calibration can usually be rectified by increasing the frequency of the recalibration. So you can recalibrate your measurement again and again in order to make it better. Then there are manual corrections of in output and reading. So in case of errors that are due to either to the system disturbance during the act of the measurement or due to the environmental changes, a good measurement technique can substantially reduce errors at the output of the measurement system by calculating the effect of such systematic errors and make appropriate corrections to the instrument readings. And uh, this is not necessarily an easy task, and it requires all disturbances of measurement system to be quantified. So this process is carried out automatically by intelligent instruments, but you can do it manually as well. Now that we have discussed about intelligent instruments, let's see some of them. So these so-called intelligent instruments contain extra sensors that measures the value of environmental inputs and automatically compensate the value of the output reading. So they have the ability to deal with effectively with the systematic errors in measurement system, and error that can be attenuated to very low levels in many cases as well. Now let's quickly discuss in the quantification of the systematic errors, because it is very important task. So once all practical steps have been taken to eliminate or reduce the magnetic magnitude of the systematic errors, then the final action requires to the estimate the maximum remaining error that may exist in the measurement due to the systematic error. But unfortunately, it is not always possible to quantify exact value of the systematic error, particularly if measurement are subjected to unpredictable environmental conditions. So the usual course of action is to assume midpoint environmental condition and specify the maximum measurement error as plus or minus x% of the output reading to allow for the maximum expected deviation in the environmental conditions away from the midpoint. And the data sheets supplied by the instrument manufacturers usually quantify the systematic errors in this way, and such figures take account of the all system errors that may be present in the output readings from the instruments. Now let's see the random errors. So random errors in measurements are caused by unpredictable variations in the measurement system, and they are usually observed in small perturbations of the measurement either side of the correct value, either positive or negative, either side, right? And they occur in an approximately equal number of series of measurements made of the same constant quantity. So therefore random errors can largely be eliminated by calculating the average of a number of repeated measurements, and provided that the measurement quantity will remain constant during the process of taking the repeated measurements. So this averaging process of repeated measurement can be done automatically by intelligent instruments, and the degree of the confidence in the calculated mean median values can be quantified by calculating the standard deviation of the variation of the data, and these being parameters are described in next lecture whenever we discuss about it. So we will keep today's class till here. Next class again we will start from random errors, and the discussions of mathematical terms like mean median and mean median range standard deviation. So if you have any doubts related to today's class or any other class, please mention them in the comment section below. If you have any suggestions or feedback for me, please mention that in the comment section below. Despite of whether it is good or bad, any type of feedbacks and suggestions are welcome. If you want me to make a particular video on particular topics, please mention that as well. So I will try to answer as many comment as possible as soon as possible. So until next time, take care of yourselves. Thank you very much for listening, and goodbye for now.